for coming. I'll be talking to you about synchronous tasks, most specifically about Celery. So yeah, I'm Filipe Ximenes. Shima is my nickname, and you can find me on Twitter as Shima. I'm from Recife, that's a city in Brazil, northeast. And yeah, and I work at Vinta, so I'm one of the partners there, and we are a service company from Brazil. Most of our clients are from the US, New York and San Francisco majorly. And we have a team of 11 experienced developers, and we work with Django and React. This is the link to our playbook. We compile there a lot of information about how we work and the things we do, so feel free to go there. We also do a lot of open source. So here are some projects you might be interested in. There's our boilerplate. It's a Django React boilerplate. We have Django roles permission, Tapioca, and there is a few others on GitHub, so feel free to grab them. All right, so let's start with some context. In broad terms, the reason we use async tasks is because we want to answer quickly to our users. Here are some reasons, some situations where we might want to use async tasks. The simplest case will be when we want to delegate long-last CPU jobs. But the most popular reason people use async tasks is probably to execute external API calls. Whenever you depend on external service, you no longer have control over how long things will take to be ready. It might also be the case that it will never be ready. The system you rely on might be down or broken. Another good reason to use async tasks is to prepare and cache values. And you can also use them to spread bulk database insertions over time. This can help you not to DDoS your own database. Cron jobs are also another good example of things you can do with them. Let's talk a little about how they work. The problem of running async tasks can be easily mapped to the producer-consumer problem. Producers place jobs in a queue. Consumers then check for in the head of the queue for awaiting jobs, pick the first one, and execute. There are many tools available to manage async tasks in Python. Our queue seems to be getting a lot of attention lately, but Celery is the all-time champion so far. So let's talk about Celery. First of all, let's introduce the correct naming to our components. From now on, producers will be web nodes, our queue will be called broker, and consumers will be workers. Since workers can also place new tasks in the queue, they can also behave as producers. Now that we have the basic components, we can dig a little deeper. The concept of a broker is very simple, but how do we implement this in a computer system? There are many ways to do this. One of the simplest would be to use a text file. Tasks can hold a sequence of job descriptions to be executed. Therefore, we could use them as the broker of our system. The problem with text files is that they are not made to handle real application problems, such as network and concurrent access. Because of that, we need something more robust. SQL databases, on the other hand, are capable of running in a network and dealing with concurrent access. The problem with them is they are too slow. NoSQL databases, on the other hand, are quite fast, but many times they lack reliability. So when building queues, we should use fast, reliable, concurrent-enabled tools such as RabbitMQ, Redis, and SQS. Celery has full support for RabbitMQ and Redis. Although SQS and Zookeeper are also available, they are offered with limited capabilities. Let's now talk about web and worker nodes. On the left, we have the code that should run asynchronously, that goes on the worker node. On the right, we have the code that places the request for a job to run. This normally goes on a web node. In this example, the web node places an add job and waits for the result to be available. When the response is ready, the result is print. Now I have a Django example. In it, the web node is requesting the number of attendees of the event to be updated asynchronously. Notice that we are passing the event objects to the task. Don't do this. Objects get serialized and stored in the broker. They are then deserialized before passing to the task. Passing complex objects, such as model instance as the parameter, comes with a few problems. First of all, in node versions of Celery, Pickle was used as the default serialization method. As some of you know, Pickle has security vulnerabilities. By allowing complex objects, you are increasing the chance of getting exposed. Later versions of this, of Celery, address this by using JSON as the default serialization method. Another issue is that database objects you pass might have changed between the time you place the task and the time it gets executed. In that case, you'll be working with an outdated version of the object. What you want to do is to pass the ID of the object and fetch a fresh copy from the database. We've been calling delay and get together all the time, but they are two separate things. Delay places the task to be executed by a worker and returns a promise that can be used to monitor the status and get the result when it's ready. Calling get in that promise will block the execution until the result is available. The add task has to store the result somewhere, and then whenever it finishes, it will be accessible to the process that triggered the task. This means that we missed some piece of the architecture. Besides the web, broker, and worker nodes components, there is also a results backend. The results backend will be used to store the task results. In practice, you can use the same instance you are using for the broker to also store results. There are other technologies besides the supported broker options that you can use in the results backend. But there are some differences depending on what you use. In Postgres, for example, the get method will do polling to check the result when the result is ready. In other situations, such as for Redis, this is done via pub/sub. We've seen how to execute tasks and how Celery works. But the real hard problem about sync tasks is handling errors. How to be prepared for bugs and failures. We are now going to go over two concepts that are essential for that matter. If you are to learn something from this presentation, learn them. The first one is idempotency. Idempotency is the property of certain operations in mathematics and computer science that can be applied multiple times without changing the result beyond the initial application. Multiplying by 0 and multiplying by 1 are two examples of idempotent operations. Once you multiply by a number by 0, no matter how many times you do it again, the result will always be 0. It's the same for multiplying by 1. No matter how many times you multiply a number by 1, the result will never change. Let's do the same for HTTP. Which of these methods are idempotent? Getting a resource should not produce changes in it. So get is idempotent. Post is used to create resource. Well, at least that's what you used to do before GraphQL. So every post request produces a change to the state of the application. Therefore, it's not idempotent. You cannot expect subsequent post requests to keep the application state the same. Put is a great example of a idempotent operation. The first put request you make produces change to the state. But if you keep repeating the same request, no changes are expected. Delete is a bit of a gray area. From the application state perspective, it is idempotent. From the response perspective, the first call might return 204, while the next one might return 404. So it depends on how you view it. The second concept is atomicity. An atomic operation is an indivisible and irreducible series of database operations such that either all occur or none occur. Despite its being commonly associated to database operations, the concept of atomicity can also be applied in other contexts. In the first box, we have a task that sets the user status to updated, saves it, makes a request to Facebook, and only then updates the username. This is not atomic. If the request fails, we are going to have inconsistent state in the database. The right way to do it is to first make the request, then update the user status and username at the same time. Another way to improve atomicity is to write short tasks. In the first example, we are iterating and sending emails to all users in a single task. If one of them fails, the task will stop, and part of your users will receive the email, and the other part will not. In the second example, we iterate over the users again, but delegate the sending to another task. If one of the emails fail, it will affect only one user. The other advantage is that it's easy to rerun a task when it's failed. The order there's an overhead on creating initialized tasks. Making them too fine-grained may harm performance, so keep in mind when you're designing. So I just told you about how you can retry a task that failed. A fairly common situation is for tasks to fail while interacting with external systems that are not available. Celery provides a retry method that can be called inside a task. This will make it try again to execute the task. In the example, we are fetching the user likes from Facebook. If it fails, we wait 10 seconds and retry. If your tasks are idempotent and atomic, you should have no problems calling retry as many times as you need until the task succeeds. If they are not, retry may produce inconsistent states or can end up spamming your users. There are some other caveats to retrying. In the previous example, the request to Facebook might be failing because Facebook is under attack. So it might be a good idea to back off and give it some space to recover. You shouldn't kick a man on the ground. Another good idea is to make the interval between retries grow exponentially. This will increase the chances of things getting back to normal before your next try. Also throw in a random factor. Imagine having 100 tasks failing and retrying at the same time. The overflow might actually be the reason why the system you are interacting with is down in the first place. All right. This is something I actually learned about the first day of the conference. I was chatting with David Baumgold. So if you use a Celery 4, you can actually cut down a few lines of code by passing a auto-retry for parameter. You can do the same thing I showed before, just using the auto-retry for and passing the classes, the error classes. I also learned that they've just got a pull request approved for a retry backoff parameter. In the next Celery release, we will be able to use retry backoff along with auto-retry for parameter and get exponential backoff out of the box. So thank you, Dave. Another common issue are tasks that take too long to execute because there's a bug there or we have a problem with network latency. To prevent this from harming the performance of your application, you can set a task time limit. Celery will input the task. Celery will interrupt the task if it takes longer than the time you set. In case you need to do some recovering before the task is interrupted, also set task soft time limit. When that runs off, Celery will raise soft time limit exception, and you can do some preparation before the task is killed. The X-late setting is also something you should know about. By default, Celery first makes the call, marks the task as run, and then executes it. This prevents a task from running twice in case of an unexpected shutdown. Having idempotent and atomic tasks will give you the ability to turn on accelerate staffing. By doing so, Celery will automatically rerun the interrupted task once it recovers. We've talked a lot about how to actively handle errors, but we all know that bugs are inevitable. Bugs in a web application are generally easy to spot. If something breaks, your user will get a 500 page, and they will find a way to let you know that something went wrong for them. For a sync task, this is not always the case. In many situations, we'll be dealing with things that do not directly affect the user experience. This means that you should be extra careful with monitoring tasks. Monitoring will help you to capture errors early and not when they are already too late. Starting from the basics, logging. Make sure you log as much as possible. This will help you tracing what went wrong when bugs arise. As usual, be careful not to expose sensitive information in the logs. This is a security threat. Logging is a general advice for any kind of application, but especially important for tasks, as they have no user interface and debugging them is harder. Make sure people get notified when things fail. Tools such as Sentry and Opbit can be easily integrated to Django and Celery and will help you monitoring errors. You can also integrate them with Slack so you get notified every time something goes wrong. Make sure you fine-tune what produces notifications. Too many false positives, and your team will stop paying attention and let actual errors pass unnoticed. Have a well-defined process to deal with those errors. Make sure they are included in the backlog and prioritizing accordingly. Floor is a tool for live monitoring Celery tasks. It allows you to inspect which tasks are running and keep track of the executed ones. It's a standalone application and definitely worth using in bigger projects. Django's SolidBits status is something that just came out. We didn't talk much about scheduled tasks, but they are not trivial to monitor and test. The cron tab API is sometimes confusing and might lead to mistakes. And this is also a project from Vinta. Django SolidBits status will add a page to the Django admin interface. In it, you'll be able to see all scheduled tasks along with their next ETA. This will give you a little more confidence that you got things right. Testing and debugging tasks can be harder than what we are used to in normal web applications. But there are a few things you can do to mitigate this. Task always eager is a setting that comes very handy for testing and debugging. This code is from the Celery source. If you had the task always eager setting set to true, whenever you call delay or apply a sync, it will run the test synchronously instead of delegating it. This will simplify debugging in local environments and facilitate automated testing. This last thing is actually more of a fun fact. So it turns out there is a PDB for Celery. RDB will allow you to telnet to a breaking point and live debug it. To be honest, I've never used it, and I'm not really sure what situation you would use it, but I'm sure someone will find it handy. All right, so time to recap. First of all, don't use complex objects in task parameters. This will help you avoid insecurity and inconsistency issues. Write idempotent and atomic tasks. You want to be able to freely rerun your tasks. Back off when you try. Other systems may need some space to recover. Make extensive use of monitoring tools. Tasks that are harder to debug. Collect as much information as you can. Get notified when something fails. But be careful to only notify when something important happens. And last, use task always eager for testing and debugging. The last thing I want to show you is something that I've built in process of making this talk, So Celery test checklist has a compilation of the things we talked about. You can actually click through the items as you verify what are missing in your tasks. And it's also open source, so you are very welcome to contribute and improve it. That's it. Thank you. I've got some, the links to the slides are there. So it's /Vinta 2017. There is also the link to Celery test checklist, my contact information, and we have a newsletter. If you want to sign up to this, the link's there. Thank you.
Thank you so much, Filipe. If you have questions for him, definitely chat with him afterwards or during the sprints. They'll be happy to work together. All right, thank you. And we're about to have closing, so hang out. Closing happens here.